Hello everyone and welcome back to the Regents Chemistry Review Series. In this video, we're going to talk about thermochemistry. So a lot of the things that we are going to talk about in this unit might be a quick review from some of the previous units, but then there's also some new things. So thermochemistry is the branch of chemistry that investigates thermal energy, which means that the heat energy that is absorbed or released during reactions. So a quick um, not quite review, but just a more general knowledge kind of thing as we are talking about thermal energy is that sometimes you might see some other forms of energy mentioned somewhere. So there are some other types of energies. For example, we have chemical energy, which is the energy of bonds breaking or forming. So this has to do with the chemical reactions. The mechanical energy is the energy of movement. So this, but it normally deals with very specific types of. So if you're talking about the movement of, let's say, particles or stuff, then that would be kinetic energy. But if you're talking about the movement of bigger bodies or machines, then that would be mechanical energy. Electrical energy is the energy based on the movement of electrons, and nuclear energy is when we do nuclear reactions. So that's when we convert the mass of our reactants into energy. So let's think back about calorimetry that we talked about in one of the previous units. So in case of a calorimeter, this is something that we can use to measure the heat absorbed or released in a chemical system. So normally what we do is we use like an insulated substance. So it's normally a styrofoam cup, but sometimes we also have like other insulators that we can use, and then we put a hotter substance which acts as the system, and we put that in most cases in water, just surrounded by any type of solvent or something which acts as the surrounding. So the system is the object that is under investigation. So that's like the hotter object. And then we are trying to see if the hotter object is going to transfer its thermal energy to its surroundings. So surrounding is what we are measuring to notice any changes in the heat, to see if the surrounding has absorbed or released the heat from to or from the system. So if you want to try to figure out if the system is absorbing or releasing heat, we do some math. So we look at the difference in the temperature, and then we find the mass of the system and the surrounding, and we can plug all of the values in this equation, Q equals mCat, which is given in table T, to figure out if the system absorbed energy or released energy. So remember, quick reminder that if the Q was a positive number, then that means it's an endothermic reaction. And if the Q is negative, then that means it's an exothermic reaction. So endothermic means heat is absorbed, exothermic means heat is released. So let's talk a little bit more about the calorimetry then and about the Q equals mCat equation. So in this equation, Q is the heat energy, which is measured in joules. So joules is the unit for heat energy, and it measures the amount of heat energy that is absorbed or released. And as I just said, if it's negative, that means exothermic; positive, that means endothermic. M represents the mass, which is measured in grams. If in some cases you might get a question where you are not given the mass in the question and instead you're given the volume, you can use the density. So D equals M over V. So if we are dealing with water, then the density of water is just 1 grams per centimeter cubed. And if we are, if let's say you're dealing with any other substance, they are most likely going to give you the density in the question. If let's say they give you maybe like iron or something in the question, and they give you the volume of iron, and they also do not give you the density of iron, that's because iron is a metal, it's an element, and you are given the densities of the elements in table S. So in that case, you can go to table S to find the density of iron and use that to determine the mass. So C is the specific heat capacity, which is basically the amount of energy that we need to raise the temperature of 1 gram of any substance to 1 degree Celsius. So for water, it's given in table B, 4.18 joules per gram. I believe your table gives it to you in Kelvin, but it can also be in degrees Celsius. The number stays the same. And then delta T is the change in temperature. Very, very important. It's supposed to be final temperature minus initial temperature. Please do not do initial minus final. And this one can be in degrees Celsius or Kelvin. And we this is basically the difference in temperature is what gives us the most, or let me just say, the difference in temperature is what determines if the reaction is endothermic or exothermic, because this is what's going to make our value, our Q value, positive or negative. So remember that in the way calorimetry works is that it's based on the law of conservation of energy, which means the energy that is lost by one substance is going to be absorbed by the other substance. So the thing that is hotter, because that's how the heat transfer works, the thing that is hotter is going to release energy, and that energy is going to be absorbed by the colder object. So energy it always transfers from high temperature to low temperature. So how about if we are in a situation where we cannot use calorimetry, or where we cannot use the Q equals MCAT equation? So for example, this equation would not work if there's no change in temperature. For example, if you are looking at phase changes. So I hope you all remember those heating and cooling curves that we talked about, right? Which look like this. So we said that the straight lines in these curves represented the phase change. So during those straight lines, there was no change in temperature. So that means if you're having a phase change, we cannot use the Q equals MCAT equation. And also calorimetry, like that instrument in general, and this whole experiment thing cannot be used if we are working with something that involves fire, because then we will have the chance to we'll either have the fire hazard, it can burn the calorimeter, or we are also using the water in the system, so the water can just extinguish the fire, and so whatever reaction it is that we are trying to look at will not go through. So for those circumstances, we have some other equations that we can use depending on whatever type of changes are occurring, or what type, more specifically, what type of phase change is occurring. So if we have melting or freezing going on, then we can use the heat of fusion, because heat of fusion measures how much heat we need to melt or freeze 1 gram of a substance. So the equation is Q equals MHF, which is also given in table T, and for the water, we are given the heat of fusion in table B. It's 334 joules per gram. Heat of vaporization, as you might have guessed from the name, is the amount of heat that we need to boil or condense 1 gram of a substance. So the equation for that is Q equals MHV, and this one, the value for heat of vaporization of water is also given in table B, and it's 2290 joules per gram. So besides using these three equations, we also have some other ways of figuring out if we have an exothermic or an endothermic chemical reaction. So for, let's say we are only focusing on chemical reactions and not physical, maybe. So if you look at table I, this table gives you something that we call enthalpy. So enthalpy is the change in the heat of the reaction. So this tells you if the heat was absorbed or released by the system. So the equation for enthalpy is the heat of products minus the heat of reactants. So the idea is that if you have a positive enthalpy, positive delta H, that means we had an endothermic reaction, meaning heat was absorbed. So which is why the heat of the products was much higher compared to the heat of the reactants. So I should write it here, that the heat of the products is higher than the heat of the reactants. And then if we have a negative delta H, that means the heat was released. So in this case, heat of the products was lower than the heat of the reactants. So heat of formation is kind of another term that we can use for delta H or for the heat of reaction, which is basically just the energy that it takes us to perform this reaction with 1 mole of the substance. So let's focus on this first reaction that is given to you in table I. So for the combustion of 1 mole of methane, this equation is for 1 mole of methane. So for combustion of 1 mole of methane, this is the delta H. It's negative 890.4 kilojoules. So because it's a negative number, that tells you that the reaction is exothermic, meaning heat is released by the system. But if I ask you for the combustion of methane by 1 mole of oxygen, notice that this equation is for 2 moles of oxygen. So if I am focusing on 1 mole of oxygen, we will divide the negative 890.4 by 2, so that we have 1 mole of oxygen, or so that we have the energy using 1 mole of oxygen. So this is also a negative number, meaning that's going to be an exothermic reaction. What if I ask you to give me the heat of reaction for the formation of methane by carbon dioxide and H2O? So what I'm asking here is that when I combine carbon dioxide and water to form methane, what will be the heat of reaction for that? So this means that I'm looking at the reverse reaction of this, because I'm combining carbon dioxide and water to make methane and oxygen. So in this case, we are just going to look at because we are looking at the reverse reaction, we are also going to reverse the sign of delta H. So now it's going to be positive 890.4 kilojoule. So that will be an endothermic reaction. So this was another way to determine if the reaction is exothermic or endothermic. Now, very, very important thing to remember is in nature, what type of reactions are favored. So let's first review some of the information that we know. So we know what enthalpy is. We just learned that it's the heat of the reaction, heat of products minus heat of reactants. And then there's also something else called entropy. You might see the symbol delta S for entropy. So just don't get confused. It just means entropy. So entropy means the randomness or disorder in the system. So notice the more the particles are kind of disorganized, the more randomness there is, the higher the entropy is. So if we have a positive delta S, that means we have very high entropy, more disorder. If it's negative, that means less entropy. And there's less disorder. So solids have very, very low entropy because the particles are very packed together. Gases, on the other hand, have high entropy because the particles have a lot of distance. So they are very unorganized. So compounds, if you think about them, have low entropy because compounds have bonds, right? And so the bonds kind of bound the elements. So if we compare them to the free elements, because they are free, they are going to have high entropy. They're free to go wherever they want. They're not bonded with something else. If you are looking at any chemical equation and we are trying to figure out which side of the chemical reaction has a higher entropy, the reactant side or the product side, then we are looking for the one that has more molecules, because the more molecules there are, there's more chance of just more disorganization. So the side with more molecules is going to have a higher entropy. So how do these two things relate to the type of reactions that are favored in nature? In nature, and this question, there's like a 99.9% chance that you are going to get this question on the exam. So please do not get this one wrong. So in nature, the reactions that have very, very low entropy and very, very low energy and very, very high entropy are favored. So high entropy kind of makes sense because things in nature are not always super organized, and it also takes a lot of effort to organize things. So randomness takes less effort. So that's why high entropy is favored. For low energy, you can think about it by comparing two reactions. So let's say we have reaction number one that needs a lot of energy, and reaction number two that needs very less energy. Um, Now we need energy to start both of them. The one that needs less energy is going to be started first. So those are the reactions that are favored in nature, the ones that need less energy because they can happen faster. So make sure that um, we always remember this thing. So exothermic reactions, the ones that release heat, and spontaneous reactions, which are the ones that do not require a lot of energy to occur, those type of reactions are favored in nature, um, because again, they don't require that much work to happen. So let's talk about a little bit more about the reactions by looking at something that we call the potential energy diagrams. Now, potential energy diagrams look like this. One of them represents an exothermic reaction, the other represents an endothermic reaction. So if you look at this first diagram, we notice that the reactant seems to have higher energy than the products. So if the reactants have higher energy than the products, that means by the time we got to the products, we lost some of the energy along the way. So this one represents an exothermic reaction. Okay. And then in the second diagram, we have the reactants have less energy compared to products. So that means in order for the reactants to convert into products, they need to absorb some energy. So that is going to be an endothermic reaction. So a few more things about the particle diagrams. If you just see that arrow number 1 that I made for both diagrams, so that is going from the x-axis to the reactants line. So this represents the heat of the reactants, okay? Or let's just call that the energy of the reactants. And then that little top, the curve all the way at the top, that is the activated complex. So activated complex is kind of like an intermediate situation, but this is the point that the reactants must accomplish for to convert into the products. So if the reactants are not making an activated complex successfully, the reaction does not occur. So even though it's intermediate and even though it's temporary, it is still the most important part of a reaction. So the energy of the so this arrow that is represented by number 2, that is the energy of the activated complex. Okay, so we start that all the way from 0 to the activated complex. So that if you're ever asked for the energy of the activated complex only, you just go from 0 all the way to the top of that curve. So the amount of energy that the products have, once again, go from 0 to the products line. So that is represented by that arrow number 3 in our diagrams. Then when we are going from the reactants to the activated complex, as we can see, to go from reactants to activated complex, we need to absorb some energy. That energy is called the activation energy. If the reactants do not absorb that activation energy, they don't make the activated complex, and so they don't convert into products. So activation energy is one of the most important parts of reaction process. So if you are asked to calculate the activation energy of any reaction, you are going to go from the reactants line to the activated complex, because remember, we are starting from the reactants. So the reactants already have a specific amount of energy. So you don't need to start from 0. Start from the reactants and look at how much energy do they need to absorb to get to the activated complex. So from the reactants to the activated complex, that is your activation energy. So if you're looking at the forward reaction, then we go from the reactants to the products. But if you are asked for the activation energy of the reversed reaction, then in the reverse situation, remember that your products are what you're starting with. So those are going to act as your reactants and these are going to act as your products. So in this case, they will be represented by arrow number 5, because for the reverse reaction, whatever your reactants are, you're starting from that and you need to get to the activated complex. So lastly, your delta H, the enthalpy or the heat of the reaction, which is represented by delta H, is going to be the difference between the heat of products and the heat of reactants. So that is going to be represented by arrow number 6 in both of these. You can also, in most diagrams, they might give you like this dotted line between the reactants and the products. So that is going to help you kind of notice that the difference between the reactants and the products is our heat of reaction. My lines are not straight, so just never mind them. Alrighty, so these are our potential energy diagrams. Let's do some more fun stuff with these potential energy diagrams. What if I ask you to draw the potential energy diagram of a catalyzed reaction? So right now what we have on our screen is just like a regular reaction. So remember, catalyst is something that speeds up the reaction, and the way the catalyst does that is by lowering the activation energy. So that creates an alternate reaction path. So if we are looking at this diagram over here, first of all, remember that these are your reactants and these are your products, right? And because the reactants have less energy than the products, that means in order to go from reactants to products, the reactants need to absorb a lot of energy. So this represents an endothermic reaction. Here at the top, we have our activated complex. So that is the amount of energy, that was the amount of energy that all of this was the amount of energy that the reactants needed to absorb to convert into, make the activated complex and then convert into products. But now that we are adding a catalyst, let me use a different color for my catalyst. Let's do blue. Okay, so for the catalyzed reaction, it's going to lower the activated energy, so that's going to be somewhere around here. So this blue line is representing our catalyzed reaction. That is catalyzed. So what this is going to do is, because it has lowered the activation energy, so now instead of absorbing all of that energy, we only need to, the reactants only need to absorb this much to reach the activated complex, because your new activated complex is here, and then it can convert to products quicker than the previous path. So the similarities that we notice between these two reaction paths are the heat of the reactants, because remember, heat of reactants is still the distance between the products and the reactants. So this arrow is still going to be the same. The heat of the products is still going to be the same because we did not change that line. The heat of your reactants is still going to be the same because we did not change that line. And then the differences, however, are going to be the energy of the activated complex, because we changed the location of the activated complex. And the second difference is going to be the activation energy, which is now going to be lower than the previous reaction path. Alrighty, so that was it for the thermochemistry. I will see you in the next one.